Okay, so this is our third video for this module on energy in the atmosphere. And I want to talk a little bit more about the reflection of the sun's energy. So I mentioned that we would talk a little bit more about reflection and how that relates to your term albedo. Okay, so albedo refers to the reflective quality of something. The reflective quality of something. So we all should be aware that various surfaces have different reflective qualities. A mirror is something that reflects perfectly the light that hits it. And so if we are looking in the mirror, what's entering our eyes is a reflection that's hitting the surface. But other aspects, like if you walk past a window, you can kind of see your reflection. When you take all of the visible wavelengths of the sun and combine them, you get white light. Okay, so it looks white to us. If you separate out the wavelengths, like in a rainbow, because the wavelengths are basically being refracted at different angles in a water droplet, so it separates out the wavelengths and we get the separation of the wavelengths as colors of the rainbow. If we combine them all the wavelengths together, we get white light. So depending on what wavelength something reflects, it can appear to be different colors. For example, the chlorophyll in plants don't absorb the green wavelength and it reflects it. So that's why it appears green. The leaves and vegetation appear green to our eyes. So the color of your shirt happens to reflect that certain wavelength, depending on what color it is. If it reflects all the wavelengths, it appears white. If it absorbs all of the wavelengths and doesn't reflect them, it appears black. So this has to do with albedo because the reflective quality of something, if something reflects a lot of the sun's light, all of the wavelengths, it's going to appear white. If it's absorbing most of the wavelengths and the sun's energy, it's going to appear black to us. Albedo is given in percent. So 100% albedo would be 100% reflection of the sun's energy. And so it's going to be somewhere between 0 and 100, but in the natural system, we don't really have 0 and we don't really have 100. So think of in our physical environment, what appears the brightest white? What appears the brightest white? Okay, so you might say snow, ice, clouds, bright white clouds, and yes, those all have very high albedo. Snow, for example, has an albedo between 80 and 90%. Okay, so it's really high. That means that the sun's light that hits those surfaces, most of it is being reflected. 80 to 90% of it is being reflected. So only 10 to 20% is being absorbed. So it stays cooler. It doesn't absorb a lot of the sun's energy and heat up and melt. It reflects most of it. Now think of something that's really dark in our physical environment. Okay, so one of the darkest things is actually man-made, and that's blacktop. And blacktop only has a 5 to 10% albedo. So it is reflecting most of the sun's, it's absorbing most of the sun's energy and only reflecting 5 to 10%. That means that black surfaces are absorbing more energy and heating up more. whereas white surfaces are reflecting most of the energy, not absorbing very much, and not heating up as much. So you probably have experienced this, I hope, as a kid playing in your front yard in your neighborhood, and it's summer and maybe you're running around barefoot. It's fine to be on the grass. It's a little bit warmer on the sidewalk, but step out onto that road and oh my gosh, it's hot as heck. You have to run really fast. You burn your feet. So look at the albedo of the sidewalk compared to the street, the blacktop. It's a very big difference. And so you are experiencing the impact of albedo on the warming of the earth. So there's albedo in our atmosphere. Clouds have a very high albedo. That's why they appear white to our eyes, is because they're reflecting all of the sun's light. So all of that light is hitting our eyes. So a lot of it, if there's clouds, a lot of it goes up back into outer space of the sun's energy and less gets to the surface. And so there's less heating of the surface. Then what light does get to the surface, of course, and then hits it, depending on the albedo of the surface, some of it's going to be absorbed and some of it's going to be reflected. So albedo is really important in how the earth heats up. And remember, as the earth heats up, it emits its own wavelengths, long wavelengths, and infrared, not in the visible spectrum, not in the ultraviolet, not short wavelengths, but long wavelengths. Here's why this is so important to understand the difference between shortwave radiation and long wave radiation. And the reason is that the molecules in our atmosphere deal differently with wavelengths of energy, different wavelengths of energy. So our composition of our atmosphere is really good with letting that visible light in. We were talking about that. It scatters a lot of the blue light, for example, but it's really good at letting it in, which is why when the sun is up, everything looks bright, why the moon looks white and also reflects some of that energy back on Earth at night. So here is the thing. It's not the sun's energy that's directly heating up our lower atmosphere. So when we have a hot day, this is, if we get in the shade, it feels cooler because the sun isn't hitting our skin and our skin's not absorbing it and heating up. But the air itself is warm. It's not like it's cold under the shade, right? It's not heating, it's not being directly heated by the sun. Our atmosphere is heated by long wave radiation. So it's actually our infrared long wave radiation that's being emitted by the Earth that interacts with certain gases in the atmosphere that absorb that long wave radiation. They don't absorb the short wave radiation. They absorb the long wave radiation. And as they absorb the long wave radiation, they heat up and they also emit long wave radiation. Now, some of that long wave radiation will be directed out to space, some to the side, right? Just like when something is emitting energy, whatever it is, it's emitting energy in all directions. So the gases in our atmosphere, the Earth is emitting its long wave radiation. The gases in our atmosphere are absorbing it, and then they emit the long wave radiation. Some of it goes out to space, some of it heats up things surrounding it, and some of it gets redirected back to Earth. So it keeps this warm energy because we can feel the long wave radiation. If you sit next to someone and they're radiating heat, which they are, you know it gets really hot. In fact, that's one of the reasons why they say when it's really cold, get naked in a sleeping bag with someone. Seriously, it works. You are sharing your radiant heat. It gets trapped in there and it warms it up. That's why a jacket works. That's why a a sleeping bag works. You're trapping that radiant heat. So the gases in our atmosphere are also good at trapping radiant heat, but not this 99%. That does not trap the long wave radiation. It doesn't. It's only these tiny trace gases that are absorbing that long wave radiation and keeping us warm. It's incredible how little of the gases make such an amazing difference on the temperature and life on this earth. We call these gases greenhouse gases because they act similar to a greenhouse, and therefore the influence on temperature is referred to as the greenhouse effect. Okay, let's write that. Okay, first let's talk about these greenhouse gases. What are they? Which gases are they? They're not nitrogen, they're not oxygen, they're not argon. Here's what they are. First of all, in order, the number one greenhouse gas in terms of abundance, get ready for this. Water, H2O, as a gas, is a greenhouse gas. It's excellent